Okay. So I titled this thing Nonpolar and Polar Molecules in IMF because the intermolecular forces of attraction have everything to do with polar and nonpolar molecules. Oh boy. Let me correct the attendance because otherwise they're going to be calling you guys. Sorry. You guys that are late, try to get in early because being second period, I kind of have to take attendance right away, and which I did. But, you know, if you come in late, now I have to redo it. Otherwise, they're going to be calling you guys and not happy about things. All right. So I wanted to start this by just listing a review of some of the content that we've done this project and how they interact. But I also wanted to say, I'm going to jump right into, I'm not going to review all the old content because I want to jump right into intermolecular forces of attraction. And my little background story about that is when you get out into the workplace, or you may have already experienced this, a lot of time bosses, at least my bosses when I worked at GE, want to know the answer first, and then you can explain how you got there or the evidence that you have and all that. It's kind of like the claim, evidence, reasoning thing. You put the claim right out there first because a lot of times your bosses and managers are A-type people. They don't want to wait through all the stuff that you did to get to the answer. They just want to know what's the answer. So because of that, and I wanted to do IMFs, I'm going to jump right into what IMFs are. And then after that in this slideshow, I'm going to review some of the background that gets me to that point. Yeah, so I just wanted to let you know that. And this is all the background stuff kind of listed in order on how I would like logically think of the content. So intermolecular forces of attraction are between molecules. So there's a couple of things that you have to kind of keep in mind or realize when I say molecules. And that is, for one, they are covalent compounds. Molecules are covalent compounds. And number two, they're like unique kind of, units here, right? They're unique units, like an N2 molecule or a CO2 molecule. They're not a whole bunch of atoms kind of attracted to each other in a big, huge network of atoms. So intermolecular forces of attraction are between molecules. The types of intermolecular forces of attraction, or IMF, we call them, are based on the shape of that molecule. So if the molecule is symmetric, that means side to side and top to bottom. If I can cut the molecule in half, top to bottom and side to side, like this and like this. So this way they're the same, and this way they're the same. Then it's symmetric and it has van der Waals IMF. That's a type of IMF, van der Waals. Some people also call it London dispersion. If they're asymmetric, which means not the same, so obviously if I cut it in half this way, these two sides do not look the same, right? If it's asymmetric, then the type of IMF is dipole-dipole. And a specific subset of dipole-dipole, which is super important, is called hydrogen bonding. Hydrogen bonding attractions, they're not an actual chemical bond. They're just a strong attraction. Hydrogen bonding attractions are the strongest and is one of the reasons why water, so this is the water molecule, and it does have an IMF of hydrogen bonding. One of the reasons why water is such a unique and important molecule for life. There's a lot of properties that have to do with this hydrogen bonding around water that make it so unique and so important to all of us. So those are the three types of IMF: van der Waals, just van der Waals, dipole-dipole, and hydrogen bonding. Hydrogen bonding is the strongest and van der Waals is the weakest. And how you tell if a molecule is one or the other, it's based on basically their geometry, what their shape is, and what elements are, are where. All right, let's see. Okay, so continuing on, these are some properties for IMFs. So van der Waals are the weakest into attraction, so, and they happen only on non-polar molecules. So polar means basically that you have, like you guys probably learned this in physics. Polar oftentimes means like you have a thing with a positive and a negative side, right? Like a battery has a negative side and a positive side. That's a polar thing. So non-polar molecules, they don't have any positive or negative side. So let's just take this, let me use a different color. The CO2 here. Do you guys remember electronegativities? That's how strongly an atom like attracts the electrons from another atom. So if you remember, this is CO2, so COO. If you look on table S, oxygen has a higher electronegativity than carbon. So oxygen is going to have a lot higher negative charge than the carbon. And we use this little squiggle sign, partial negative and partial positive. But since you have an oxygen on this side as well, it's balanced out, it's even. So you're not going to have an overall positive charge on one side or negative charge on one side. However, this molecule here, happens to be chlorine, and this has a partial negative charge on this side, and these hydrogens have a lower electronegativity, so there's a partial positive. So you could see with this atom, right, you do have kind of a plus on here and a minus over here. So this molecule, not atom, molecule, does have poles, so it's called a dipole, a plus and a minus side. Same with water. This is oxygen and hydrogen. Oxygen has a higher electronegativity, so it's going to have a partial negative and a partial positive. Now, if you guys remember when we were talking about different bonds, is that the next thing that I have here? If you're talking about different bonds, oh, I forgot this last part. So as far as other properties goes, solubility, like dissolves like, you've heard that before. So polar solvents, polar liquids will dissolve polar solids or other polar liquids. Non-polar will dissolve non-polars. So an example are salt and sugar are both polar solids and they dissolve in water. Oils and greases will dissolve in gasoline, and all three of those things are non-polar. So like dissolves like, polar dissolves polar, non-polar dissolves non-polar. And that's super important to remember also. Okay, so this is where I was going next. This is a review of the summary between bonds. So we have ionic bonds. Ionic bonds are where the electronegativities are so different, right, that the let's see, I'm going to use NaCl like always. Okay, so the electronegativity of chlorine is so much higher than sodium that chlorine takes this electron and just steals the electron. So then you have Na plus and Cl minus, right? So it completely steals the electron away. That's because the chlorine is so much stronger than sodium. It's kind of like a bully, right? However, if I got something like carbon and oxygen, oxygen has a higher electronegativity than carbon, but not strong enough to like actually rip the electrons away. So when you have a carbon oxygen bond right here, down here in the covalent bonds, you're going to have a partial negative, that's that weird squiggly, is means partial negative and a partial positive charge, not a full negative and full positive, because oxygen's not strong enough to actually take away the electron, but it's strong enough that, like, you think about a tug of war, right? A tug of war, oxygen's strong enough to pull the electron closer to him, but not rip him away. So this would be called a polar bond. This is called an ionic bond. So ionic bonds are like an extreme version of polar bonds in a way. You know, they're like full-on positive and negative charge, where polar bonds are only partial positive and negative charge. You can imagine that oxygen, or nitrogen, they both have the same strength. So they're both sharing the electrons equally. Nobody gets to have that electron closer to him than the other because they're both the same strength. So if you're thinking of a tug of war, that electron is going to be right in the middle because the two oxygens or two nitrogen atoms are exactly the same strength. Sometimes you might have two elements that are close to the same strength, but not exactly the same strength, but close enough that they still call it nonpolar. You only get polar bonds when one is so strong, it's like between 0.6 and 1.6, strong enough to like have the electron closer to it, but not strong enough to actually rip it away. I know I've said this like 10 times. And I just, this chart, I think you guys saw this chart before, had coordinate covalent bonds here. And again, we're still talking about bonds, so we're only talking about between two atoms. And you don't have to know what the coordinate covalent bonds are, but I'm going to tell you anyway, just so you know. If I drew a Lewis dot structure of water, right? This is the Lewis dot structure of water. Each hydrogen has 2 electrons, and the oxygen has 8 electrons because each bond is 2. So that's a happy, stable water molecule, stable structure, right? Now I have a little hydrogen atom coming about, but somebody else stole away this hydrogen's 1 single electron. So hydrogen atom has 0 electrons, so it has a +1 charge. And as we know, hydrogen wants to have 2 electrons to be happy. Hydrogen is one of the two elements in the first row, so they only want 2 electrons to be happy. Well, what hydrogen does is hydrogen comes and finds the water molecule and says, hey, do you mind if you share? You have these extra electrons hanging out here. Will you share your electrons with me? And then the water molecule says, oh, I guess so. Sure, why not? So then the hydrogen atom says, yay, and then comes over here. Let's see, do this thing. Comes over here, right? So the hydrogen atom did not contribute an electron like this hydrogen atom and this hydrogen atom each contributed 1 electron to the oxygen. This one in red here, it didn't contribute any electrons at all, but yet oxygen's nice enough to share their lone pairs with hydrogen to make hydrogen happy. So the overall thing is that this molecule here with 3 hydrogens has a +1 charge because hydrogen didn't have an electron to donate. And so since it has a +1 charge, it's an ion, H3O plus ion. But this bond here is the coordinate covalent bond because one of the atoms did not contribute an electron to share. So that's kind of a long story there. You don't really have to know about coordinate covalent, but you do have to know about nonpolar and polar. And so again, nonpolar is that the electronegativities are similar so that the electron is shared. The electron cloud density doesn't go toward one atom or the other. But the polar, because the electronegativities are different, whichever one has the higher electronegativities grabs the electrons and makes it come closer to it, but doesn't get to rip it away. All right. So those are bonds, that means between atoms. Now we're going to think about compounds. Compounds is like the whole unit, not just between two specific atoms, but however many atoms are combined in that thing. All right, so compounds, we also have 3 compounds, and it can be confusing because the names are the same, ionic compounds versus ionic bonds. So make sure you know which one we're talking about, compounds or bonds. So for ionic compounds, we have metal and non-metal ions come together with a plus and a minus charge, and that's how we make an ionic compound. So the non-metal ions can also be polyatomic ions. So I could have sodium carbonate. That would be an ionic compound because sodium is a metal, and it takes away one, so for example, let me do this in red. Sodium Na plus, and then carbonate CO3 minus. I think it has a -1 charge. I don't remember the charge exactly, but the electron from the sodium actually gets ripped away and onto the carbonate. So this is an ionic compound, just as sodium chloride is an ionic compound, but just with 2 elements. So that's ionic compounds. The covalent compounds, in the covalent compounds, all of your elements are nonmetals, so no one atom can rip the electron away from another one, so they're all shared. And the very stereotypical example of that is water, H2O. So the electrons are being shared between the H and the O, each H and O. Okay, so that's a covalent compound. And then metallic compounds are just all metals. They could possibly be different metals. This might be an aluminum, and this might be a copper. I'm just making it up, but they're all metals. And the electrons, the valence electrons, are just kind of like floating around between the core kernel atoms, which is the nucleus plus the core electrons, and just kind of hanging out there. And that's one of the things that gives the shininess to the metals, you know, some of those really cool specific metallic properties. Also the bendiness, because these electrons are just floating around. Okay, so that's a quick review of the types of compounds. Make sure you know the difference between bonds and compounds. Okay, so we've got to close that. All right, so Lewis dot structures, we just covered this yesterday, and I'm going to do it again here. Lewis dot structures are two-dimensional structures. And you could see the compounds that we were talking about. I showed you I guess the 3-dimensional versions of them a couple of slides ago. And again, so just a quick thing again. Oopsies. Did I unshare my screen all of a sudden? Oh God, so silly. All right, I wanted to do this. So just a quick review thing here. These are symmetric and non-polar. Symmetric. And what kind of intermolecular force of attraction are non-polar and symmetric molecules?
Van der Waals.
Yes, indeed. Okay, this guy here is polar, because obviously it's not symmetric. You got this weird chlorine thing happen over there. Asymmetric. Oops, I think there's only one S, sorry. And what kind of attraction do you think is in this molecule here?
Dipole.
Yep, dipole, exactly.
Oh, sorry.
So this is Van der Waals. This is dipole. And then, so this last one here, we have, it's also polar, right? Polar. And it's asymmetric, because obviously, right? they don't look the same top to bottom, side to side. And what kind of hydrogen, or what kind of IMF do these atoms have? These molecules have? I almost said it.
Hydrogen bonds.
Yes. Okay, and let me just show you super quickly. So this oxygen is going to have a partial negative charge to it. This hydrogen, both of them have a partial positive. So the next oxygen, I don't know, I feel like I've said this before. Partial positive. And then partial negative. So this partial positive is attracted to the hydrogen, is attracted to the oxygen, which has a bit of a negative charge. This is an attraction here. Right? And so that's how the water molecules kind of, glom together. Like in a water droplet, you see the water molecules glomming together. That's because these positive and partial positives and negatives really want to come together. Okay, but these are two-dimensional drawings, right? So sometimes it's hard to see because obviously the middle one is not going to be flat. So this is an example of the Lewis dot versus the 3D structure. Now they both have advantages because for the 3D structure, let's take ammonia, for example. This structure here, well, even water. Let's take water. You might think water could be drawn like this. Oops, this is an H. So it looks like it's symmetric, right? But in reality, these electrons here, they're negatively charged and they push away the electrons that are kind of surrounding the hydrogens to make them actually bend the atoms. So the atoms look like this, and you wouldn't know what's the reason why this, this atom is bent in this weird bent shape. You wouldn't know that unless you knew the Lewis dot structure, because it's these electrons, lone pair electrons, they're called, that are forcing the hydrogen atoms to like bend down. Similarly, for this this nitrogen here, you have lone pair electrons here that are forcing the hydrogen atoms away. And you wouldn't know that with just a kind of geometrical or a three-dimensional picture unless it's done correctly. The reason is because those lone pair electrons. Oh, that's the other reason why. See how this weird chlorine is so far away from the other things here? It's because these electrons here are pushing everything else kind of away. It wants to be, negatives repel negatives. So you do have electron clouds surrounding all this thing. It's pushing it away. So that's why they drew this distance between the chlorine, say, kernel atom, and the other ones are kind of far apart from each other because the chlorine has so much negative charge that's pushing the other ones away. Again, you don't, I'm not making you know the geometry, so you don't have to be able to explain what I just told you. If you're given either a three-dimensional structure, oh, I misspelled structure, or Lewis, you will have to write a Lewis dot structure, but if you're given a three-dimensional structure, you should understand like why it has the shape that it does. So really, all these things, the covalent and ionic bonds that we talked about, which goes into covalent and ionic molecules or compounds that we talked about, that goes directly into the shape of the molecules. Now we're just looking at the molecules themselves, and that goes into the intermolecular forces of attraction, right? They all kind of like flow from each other. And the IMFs go into the properties. I don't know why I have this here. It seems like a duplication. The IMFs kind of go into the properties. So finally, just a review of the properties of compounds. So we have metals and nonmetals for ionic compounds. This doesn't have to do with IMFs at all because there are just metals and nonmetals, right? So the positives and the negatives of the metals and the nonmetals like just are attracted to each other because, you know, opposites attract. And I just put this periodic table here to remind you which the yellow ones are metals, the green ones are nonmetals. The metalloids, if the metalloids are bonded to a nonmetal, usually it's considered a covalent compound. They're kind of weird in betweens. Happily, there's not too many of them, but usually they're considered a covalent compound. So it's metals and nonmetals for ionic compounds, and they have certain properties, right? High melting and boiling point because their bonds are so strong, right? Plus and minus, full on plus and a full on minus. They're so strong. Covalent compounds usually have a little bit lower melting point. They can also, you know, some of them will like evaporate. They're more volatile than ionic ones. They have some other properties because they don't have a full negative and a full positive charge. And then, of course, metallic compounds, you guys learned these in the periodic table section also. Mainly, a lot of their compounds are because those valence electrons are just floating around amongst the kernel atoms. And so you have the sea of electrons, and that's really what designates most of the metallic compound properties. Okay, so depending on the compound, a solid compound, how they're put together, they have different, very different properties. Yeah. Okay, so let me go very quickly into a mastery thing from the rubric. Somebody asked me about this yesterday. I have time. And I just wanted to talk about that briefly. So one of the things was like lattice structure. So when you're talking about solid phase materials, you have three basic structural types. You have crystalline, where the atoms are arranged in a regular, repetitive, you know, pattern. Yeah. Then you have polycrystalline, where you have these teeny like groups of regularly arranged atoms, but within the actual overall material, they're not all in the same direction. And I'll explain that in a minute later. Visually, it'll be better. And then you have amorphous materials, and these are when the atoms and molecules don't have any specific organization. So they're not organized like in a pattern at all. They're just kind of mixed up. So you might think of, for example, like spaghetti that's uncooked. You know, all the spaghetti things are all in a row, very like regular pattern, versus cooked spaghetti. It's all like mixed up, and that's amorphous. So crystalline is uncooked spaghetti. Amorphous is cooked spaghetti. That's all mixed up. Another term that you might use for these are for crystalline solids is a unit cell, which is basically the smallest component of the repeating pattern. And then the lattice structure itself is, well, what is the pattern in that smallest unit cell? And so here's an example. For example,
can you go back to the last slide?
This one?
Yeah.
Yeah.
I just had a question.
Sure.
Is this all shared with us?
It's on the agenda, and if I forgot to share it, I'll share it as soon as I stop. I might have, you know, a lot of times I just make this in my drive and then I forget to put it in the right folder and then it's not shared, so. Okay, are you good?
Yes.
All right. Okay, so here is an example of unit cells. So these are both like unit cells. It's the smallest unit, right, that repeats over and over. And you don't have to know what these the specifics of these are, but just know that they're, you know, some specific formats that they use. And this is to identify, you know, what the crystal structure is.
So the right is the lattice.
So the lattice, okay, these are the lattice structures, different lattice structures. All right. So one lattice structure is this, it would be called, I think, simple cubic. I think this might be simple cubic. I don't have these lattice structures memorized, I'll be honest with you. So this is like the same atom, carbon, 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 carbon. I'm just saying, or so, you know, whatever it is, sodium, sodium. And this one would be a body-centered cubic, I believe. So you have a different atom here, and then, you know, different atoms on the outside. So different elements, sorry, a different element in the middle and other different atoms on the outside. So that's a pattern. That's a different pattern. Right?
So so lattice structure is just for crystalline structures.
Yeah, both unit cells and lattice structures are both for crystal, only for crystals, crystalline materials, right? The lattice structure tells you the pattern, the specific pattern that the elements, the atoms of the elements are in. And the unit cell just means it's the smallest unit of that repeating pattern. And I think, I thought I had, oops, I have to do this. Okay, so I have this as an example. This is an example that you've seen before, right? And it's a good example for, say, sodium chloride. So let's say the green ones are sodium and the purple ones are chlorine, right? So sodium chloride is easy. It's just, you know, sodium, chlorine, sodium, chlorine, sodium, chlorine. So that the smallest unit that shows the actual pattern is this, where, you know, where these are alternating, probably. Is that correct? Right? So sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. This is the smallest unit, but obviously a salt crystal that you could actually see with your naked eye is like millions and maybe even billions of sodium and chlorine atoms. But if you take salt water and just evaporate it, those atoms, when they're in solution, the sodium and chlorine ions, they're just floating around in no specific pattern. But when the water goes away, the sodium and chlorine ions, they come together as a solid, and they'll come together in this specific pattern. So if you just evaporate water and look at it, you're going to see little teeny cubes in there. You're going to see little teeny cubes. There was no little fairy that came and cut it into perfect cubes. That's just the way that the atoms of sodium and chlorine came together, because they're that's just the way that they come together for the lowest energy. All right, and so each one of those cubes, they're crystals, right? All the cubes are crystals. If I can take the smallest portion of that crystal that will still show the pattern, that would be my unit cell, and the actual pattern I have would be my lattice structure. Different materials have different lattice structures. Yeah. All right. So this is just like I promised you, a visual to be able to, in your mind, identify the different types of structural organizations. So crystalline, you can see these are all kind of very structured. Amorphous, these are all mixed up. There's no specific order to it. And then the polycrystalline, within each of these colors, right, the atoms are ordered nicely, but each of these different colors is a different crystal pattern. So it could all be the same material, they're just not aligned, you know, the whole thing isn't aligned properly or according to the pattern. Okay, so that is it for the the crystal lattice structure stuff. Again, if you're doing the mastery thing, you absolutely do not have to, know what the actual specific crystal lattice structures are. Just know that they come in specific patterns. All right, let's see. And then the last thing on this slide that I wanted you to, it would be really nice for you guys to watch this on your own. I think it's about 10 to 15 minutes, and just do it, later on at some point. It really, I think it gives a nice examples. I think they're fun. Crash course chemistry videos I think are kind of fun, but it reinforces a lot of what I've just said, but in a more fun and way. I didn't think that you could get a lot out of this if you hadn't heard this information already, because it goes pretty fast. But once you've heard it through and then watch this, I think it'll make a lot of sense. All right. Are there any questions before I let you do the chat? I mean, not chat, sorry. Two things at once. Okay, so as before, I want you to, I think you guys got it based on the couple of answers that I got to my questions, but I have a very quick check-in here. It's in Echo. I want you to do that today. I'm not accepting any late work on it. So you have to do it actually right now. I'd like you to do it right now or today. Yikes, is class almost over? Oh my God. And then last but not least, and as soon as class is over, I'm not going to take the time now to do this, but I don't think this is shared with you. No, let me just do it right now. Somebody yesterday, when I said, what questions do you have? They said, somebody said naming. So I wanted to share this with you guys, which is the assignment I gave you, but it's the answer key. So if you go down here, and hopefully this makes sense. For example, for binary compounds, which are two different elements, you have covalent, which are non-metal compounds, and you name them by using the prefix, and then the first non-metal, a prefix, the second non-metal with the ending of "ide." And here's some examples: carbon dioxide, diphosphorus, which has a prefix on the first one, pentoxide. Oh, the prefix I didn't say here, but that is how many atoms of that element there are. Dihydrogen monoxide is right here. So this is kind of like the rules. These 2 pages are the rules for naming so far. I had wanted you to organize, these boxes into rules like this. But if you are still confused, you can maybe use that for kind of a guide. Before you guys leave, oh, I think I have 4 more minutes. I would like you to, in the chat, and I'm going to use this in part for attendance as well, even though I took attendance right at the beginning. I would like you to put in the chat